In this video I will again try to optimize this oscillator with two crystals inside. I have worked with it in previous videos, Nerds 80, 83, 85, 86, 87, 88 and 89. And this is Nerds 92. In the previous video, Nerds 91, I made improvements to the two-channel receiver to make it less time-consuming to try to find the optimum of this oscillator. I have been running the measurement on this oscillator, the one with the two crystals in, for a little bit more than 14 hours now. And I'm looking particularly at very close range, 0.1 Hertz, 0.2 Hertz. And there I see these numbers. 0.1 Hertz is minus 89 and 0.2 Hertz is minus 101 dBc per Hertz. I can see the noise up to this point, 5 Hertz, because here there is a reasonable separation between the real component and the imaginary component of the average correlation. I usually take a value at 7 Hertz, but this is a bit uncertain here. The blue trace, that is the channel 1 oscillator, the one that I modified in the previous video, and it has bipolar transistors, and it is significantly worse than the channel 2 oscillator. This is 5 Hertz, and it is 1, 2, 3, 4, 5.5 decibel that differs. That is a significant difference that will make measurement times much longer, above about 4 Hertz separation, or even above 1 Hertz separation, because there I have this difference, 2.5 decibel. Very close to the carrier, this is 0.1 Hertz offset. It is the other way around. Channel 1 is much better than channel 2 by about 10 decibels. So that makes the measurement at 0.1 Hertz offset have a limited performance. The real part is here and the imaginary part is here. So this signal is a bit noisy. I have plotted the result, the red data points, together with the results that I had for the Wenzel oscillator. And the red line is the f minus 2 power minus 3. And there is a deviation here. Maybe it's infrasound, maybe it's something else. And this point is a little bit too low, about 1 decibel, but I think that is just the accuracy. This point was a bit noisy. I have improved the wall thickness of the channel 2 oscillator, since I found that to be the most important thing to avoid low frequency modulation due to infrasound. Here is a nice waterfall showing how the thermostat starts from cold here and drifts up to the proper frequency here. And it's not yet at the final position. I have to wait another 5 minutes or so. The improved wall stiffness of the box has not improved at all. At 0.1 Hertz, I still see from here to here, 82 to 72, that's about 10 decibels, just as before. I have sealed the box and made a new lid from 3 mm hard aluminium, just like I did with the channel 1 oscillator. The improvement is small. Here at 0.1 Hertz, it is 2, 4, 6, 7 decibels. And that is only 3 decibels better than before. But starting at 0.15 Hertz. That's here. Both oscillators are equally good, and the measurement, this is 11 hours, is reasonably good. The real part is here and the imaginary part is here. But measurement is going to be slow. When evaluating the box, I should start at about 0.2 Hertz. Here, statistics is going to be much better. The optimum range for measurements is then from 0.2 Hertz here, with this separation between real and imaginary part, and up to about 2 Hertz, with here to here. Higher up, statistics is going to be uncertain because the separation from the yellow to the blue is too large. So maybe even stopping at 1.5 Hertz would be better. More points, but more uncertain points. I don't know which is going to be fastest in convergency. The amplitude noise is much lower than the phase noise, up to about 2 Hertz, and from 0.2 also. So the only noise I have here close to the carriers is phase noise. And an interesting thing is that the phase noise on the signal is equally strong as the phase noise on the mirror image. It means that the phase relation for this noise is not the same as the phase relation for the carrier. And the conclusion is the noise comes from the frequency mixers. So I will check to swap the oscillators. Now channel 1 is the better one. So obviously the sensitivity for the correlation measurement in this region, around 5 Hertz, is limited by the mixers. So better mixers would be a good thing. I'm measuring the average of the yellow curve, the dB scale, from 0.2 Hertz to 3.7 Hertz. And after 392 or 94 correlation averages, that average is 134.77. 134.77. That's here. That's the average of the dB scale. And this is a straight line in the diagram, as you have seen when I plot it in a logarithmic scale. I have placed the oscillator inside this wooden box, and I have these ceilings here, so it should be quite well isolated from infrasound now. This does not work well, because the temperature is rising too fast and the frequency is drifting downwards until Linrod makes a frequency adjustment. But frequency adjustments come too frequently, so this is not practical. And further, the result I see is much worse than what I had when the unit was outside the wooden box. So something has gone wrong, and I will try to find what. The room temperature, as I find it out on the outside of the box, is about 23.8 degrees. The inside, after I just opened it, is 28 degrees, so it has increased by about 5 degrees here. Performance has not recovered. I can see that also here. In the baseband waterfall, the width of the red region here is much wider than it was before. So something is bad. I will try to clean connectors again. The only connector I have moved when moving the box inside here is this one, the output connector. I had a T connector inserted in between before to make the box a little bit lower, but that's not needed anymore. So I have cleaned this and it didn't make any difference at all. I have added a fan to blow a room temperature air stream onto the oscillator, because now when it is in the box, air circulation is not at all as good as it was before, and that means that the temperature has become higher while it is in this position. This has made an obvious difference in the close range noise. Here and here and here is when there was no fan, with and without connector cleaning and so. But before, when it was outside the box, I had this width of the shift between red and green. Here it is obviously much bigger, but here it is restored and maybe even a little narrower than what I had here. So temperature is very important for the close range noise for still completely unknown reasons. But when I look at the average of the noise from here to here, it is not good anymore. It's minus 129. It was minus 133 before. And I guess this is noise from the air streaming on the box, producing wind noise, which is in the frequency range a couple of hertz, while the mysterious phenomenon that I can see here is, if I measure it, you can see it is 0.3 hertz, which means plus minus 0.15 hertz. So that's where the difference is big. I have filled the box with canned food and placed some metal pieces, heat conductors, on the surface, all to make the heat capacity larger in the box and try to make the temperature rise of the box internal a little bit slower. The main constituent in the canned food is water, and that has a high heat capacity. The frequency first shifts upwards about equally rapidly as without all the water content. Then it continues to shift at about the same rate, but now there is much more noise surrounding the signal. And that's reflected by the sum, which is now 120. When running overnight, before it was, 130 when I restarted it after running overnight. So there is a 10 dB performance loss, and I don't think it's the temperature, it is the temperature rise probably. Something is expanding in an irregular fashion. The frequency drift is slowing down, and the noise is becoming much smaller. And the average over the entire range, up to 3.5 Hertz, is not as bad as before. The effect of all the water is becoming visible. Frequency drift is getting significantly slower here, and the noise is becoming much lower also, similar to what I had here when running overnight. And the average is now 133.5, and I reset the average collection again, here. So I start collecting again. I have glued this 4.7 ohm resistor at the position where the FETs of the amplifier for the second crystal is located. There are 5 FETs glued together. Here is the baseband waterfall, and the average correlation spectrum from 0.2 to 2.7 Hz is 133.3 decibels negative. I connect 3 volts to that resistor. It gives me 0.58 amps, and this is about 4 watts. The heat from the resistor causes a frequency drift, and here at this point there seems to be a noise burst, but it's a considerable time delay from here up to this point. The average is good, despite this latest noise pulse. I have moved the point of heating to the second amplifier stage, and I replaced the resistor with another one because the ceramic was destroyed when I tried to remove it. And I apply 15 volts to this new resistor. 15 volts, 0.35 amps, that's about 5 watts. This has caused the frequency to rise also, but it is associated with a significant increase of the noise sidebands. The average performance between 0.2 and 2.7 Hz is degraded by about 4 decibels now. Now the box is in thermal equilibrium again, and I have started collecting averages again, and this is normal behavior. After a while it will probably end up at 133.5 or something like that. I have moved the resistor to heat this part of the box, and I apply about 5 watts to it. Heating started 2 hours and 38 minutes ago. And that is 17 something. You can see here how temperature caused a frequency drift, and after a while the temperature is stable. There seems to be no significant change in the sideband noise. I have collected averages over the entire time, and that is 132.5. I will reset the averaging here. The temperature is constant now, so I see no noise because of temperature change. And the sequence starts similarly as it did the previous time. Here. At 20 averages 133.4. Now 132.6. But the statistical uncertainty is fairly large, as one can judge from the curve. I have made something from copper, a cone, because I cannot make a proper parabolic reflector easily. Inside is a 12-volt lamp. I'm running it from 8.5 volts, and it is illuminating a normal paper that I use in my printer. And I check the temperature. 35 degrees, and on the paper itself 22 degrees. So it gives a significant amount of heat. I will place this inside the box and illuminate different parts to see where is the strongest sensitivity with respect to noise generation. First I try this. I had the box open for more than 1 hour, from here to here. It has taken a long time for temperature to stabilize, but now it is almost stable. The average noise is good now, but I will turn on the lamp and clear the average spectrum, like that, and lamp on. What? I had forgotten a cable. Now I try once again. I'm clearing the correlation spectrum and switch on the lamp. And then I can see the time the lamp has been running here. Here I switched on the lamp. It is here, and in the average data, the first 6 averages was on the old data before the lamp was on, but now it measures the noise. I will clear again to get the noise while whatever is being warmed up. The phase noise from 0.2 Hz to 3.7 Hz is degraded by 3 decibels on the average, while the temperature is rising. I will wait for a while to see if there is an equilibrium with less noise. This is 20 minutes later. The average noise is almost restored. The temperature is probably reasonably stable again inside the box, and not much higher because the power is only about 2 watts from that lamp. And looking here, when the lamp was turned on, that's here, you see it much wider. And now it is back to normal. I have switched off the lamp. The frequency comes back rather quickly, but there is no significant noise increase during this switch off. I have had collected data, and first a couple of samples on the old data, and then starting here. And it comes back to about 132.2. just as I had before switching off the lamp. So I don't know what kind of conclusion I should draw of that. Maybe the temperature, the cooling rate of whatever causing the noise is much slower than the cooling rate of whatever causes the frequency drift. I have moved the lamp to a different position, shining on some other components. It seems the cooling process was very slow. Here the signal is noisy, and then something happens at this point. And now this situation has a not so good average performance, 130 only. I will wait some more time. Performance has not quite recovered. The average is minus 129 dB now. But I switch on the light again from the new position. It seems the frequency drift has slowed down now. It was going like that, and then Linrad retuned, and now it is going slower. The noise has increased a little. I see only 126.7 now. But with the other position of the lamp, that was here. You can see the strong noise when it started, and then it continues to fall in frequency even so long times. So it seems this position is heating the noise problem less than the previous position of the lamp. I will leave the lamp shining overnight and look at what happens when I switch it off. When I return in the morning, the phase noise is very high. And the average is only minus 117.5. I switch off the lamp to see whether something changes. Here is where I switched off the lamp. Frequency changes as expected. And then Linrad makes a frequency correction here. What happened at this point, I don't know. But obviously something has gone very wrong with the amplifier. There is a noisy component now. I'm checking the amplifier in the interferometer, injecting a signal through 10 pf into the sources of the 6 parallel J310. And then I look at the normal output signal, the one that I am analyzing when the thing runs as an oscillator. The carrier is attenuated by 40 decibels. Here at 0.2 Hz, I can read about minus 90 dBc per Hertz. Means that the noise is minus 130, and that is far below the numbers I'm observing. Then this is 1 over F noise, flicker noise, so it should be 3 decibels from here to here, and then another 3 decibels from here to here, and so on. When I look in the baseband waterfall, I see no irregularities. It looks perfectly nice. Now, the signal is about 35 decibels weaker than normal, and I have set the sensitivity 15 decibels more sensitive than I did before, 5 instead of 20. That means that there is a 15 decibels less visibility, but there is a 40 decibels carrier suppression. So this is a much higher sensitivity for noise than I had before. And I see nothing irregular here. I'm still running in the interferometer, injecting a signal here, but this time I'm looking at the limited output here. The signal there is significantly weaker. The limited signal is about 10 decibels weaker, so I have changed the color scale from +5 to -5 to have a similar picture. And it looks similar, and I see no particular noise bursts or so. The sideband noise at 0.2 Hz is about 89 dBc per Hertz, say 90, plus 40, that means minus 130. That is far below what is needed at close range, 0.2 Hz, as we have here. At 2 Hz, here, I read minus 106, means minus 146 dBc per Hertz. There seems to be at least 3 separate problems with this unit, and I have a feeling one of them is the infrasound. I have set a bandwidth of 0.1 Hz for the main waterfall and spectrum, and then I have these other graphs, and the average from 0.2 to 3.7 is minus 124 I will now close the box to see what happens. Here I closed the box. As an immediate response, the noise increased significantly, and then there was an event, and then the noise was lower for a while, particularly if you look at the edge here and compare before the box was closed. And now it is noisy, the noise is rising again. I guess it is the temperature rising noise that I have seen also when heating with resistors. This could be that there is some sound inside the box when it's closed. Air is leaking in or out from it. And this was before. It is more uniform all the time. And as you see here, we have now again stronger noise, but it looks different. I have placed the box upside down again. It's squeezed in this, I don't know what it's called. Maybe that helps to resist infrasound. Here I moved the oscillator out of the box and mounted it upside down. Initially there is a lot of noise, and then it calms down. Here I entered the room again. Now the noise is a little lower than it was standing the opposite with the upside up inside the box. It's now 126.7 or 8 or something. The oscillator is noisy and has been running overnight. At about 10 minutes past 8 something happened and the noise became much less. And we can see that in the main waterfall also. The oscillator has been running upside down in this wooden box for a long time now with the lid open. The average sideband noise from about 0.1 Hz up to 2 Hz is minus 125.4. After 2,200 averages and 23 hours and 46 minutes. This is the baseband waterfall and the main waterfall. I have removed the lid from the oscillator to expose it to infrasound. Then the screen looks like this. In the baseband waterfall, the width has increased significantly, but in the main waterfall, the resolution is not good enough. Here I see the sideband noise at maybe 5 Hz separation, and there the difference is very small. Then the average noise from 0.1 Hz to 2 Hz has been degraded. It is now 111. It was 125.4 when the lid on the oscillator was in place. And the reason for this is infrasound. I now close the wooden box. And that should reduce the infrasound, but it will cause a problem with rising temperature. Here I closed the wooden box, and there is a lot of noise all the time, much more than here, but much less than while the box was open. Frequency adjustment, but also something else that I don't know what might cause it. Here the average noise is 111. That's the same as I had with the box open. But this looks very peculiar, and some of these events have been included. So I reset again. Hopefully I can get a result without events in the baseband graph. The average noise is about 120 now, and the peaks here are gone. What I can see is that the noise very close to the carrier is in the order of 10 decibels stronger now as it was here, but it is only the very closest range. We have these peaks that have the green and the red trace at the same level, means all that noise comes from the oscillator, and it's not a result of the correlation. At something like 1 hertz offset, you can see that the two channels are different, because the noise from the oscillator under test is significantly smaller than the noise from channel A1 or channel 2 oscillators. But close to the carrier it looks different. Suddenly this event happened. I just made a GIF file from Linrad, so I don't have more information on what happened before and what happened later. But you can see the noise stretches all the way out here from the strongest time. I think this is an happening in the crystal. I have seen similar things with fundamental frequency crystals in the past. The power in the crystal is about 200 microwatts. I have never seen any specification what these crystals can tolerate, but I don't think I am running them at too high power. The oscillator has been running for 2.5 days, 65 hours, while Linrad has been collecting average correlation spectra. The average from 0.22 Hz up to 3.7 is stable at slightly below 134. That's what I have seen before. It seems the oscillator has recovered from whatever happened with the crystal. Despite the long time, I cannot really see the noise at 200 Hz offset. This is minus 174, and the red dots are approximately the same range as the yellow trace. So the imaginary part and the real part are about the same. Now the correlation gain is very high, and that is a warning flag. On the other hand, the correlation gain is smaller out here, so here the result is a little bit more accurate, but still the real part and the imaginary part are similar. The values I see now are these crosses, here, here, and here. About 1 decibel degraded up here, and then very close from here to here, and a couple of tenths better here. And then I have new data points because of the better statistics. And they fit to a line like something like that. The frequency is 9999.94714.5 kilohertz. I subtract 10 megahertz and find 52.854 hertz. And that means that the 50 hertz mains spur should appear at 2.85 hertz. That is what I see here. In the real part it comes negative, and it's fairly strong in the imaginary part, not with respect to the real part, but with respect to the normal value of the imaginary part. The 99th overtone should appear at 9994.7675. I have turned up the signal level to saturate the sound card slightly. That means I get a lot of overtones. And I have selected the 99th, which comes at this frequency, close to where I expected it to be. And here I can see how the frequency drifts. One division here, 0.1 Hertz, corresponds to 1 millihertz on the fundamental, or 1 millihertz at 10 megahertz. I have disconnected the PLL. This means that I see the frequency difference between my oscillator number 2 in the receiver and the oscillator number 1 in the receiver. The things that are the same here and here belong to the 2 crystal oscillator, while the higher frequency variations here belong to the oscillator here. This oscillator is much better, as you can see, and the frequency drift, the slow frequency drift, is maybe the temperature problems of the oscillator I am trying to measure. And I can see here occasionally there is a difference, that one or the other is broader, means there is more noise on the oscillators in the receiver than in the oscillator under test. Probably this information could be used to compute the Allen variation, although I don't know how to do that. But what I see here is much better than what I have seen before on this oscillator. So I'm satisfied with it for the time being. Here I can see that this peak looks ugly, while this one is better. So it means that something happens in the shorter time scale in this receiver oscillator at this moment. Here, this peak is clearly narrower than this one. Now, the correlated frequency drift that comes in the both channels, it could be instabilities in the power supply to the oscillator under test. This is not so easy to determine, however. I have reduced the transform size by a factor of 2 to get a 2 times better time resolution. It's about 10 minutes from here to here. And we can see the 2 oscillators in my receive system are very different. This one is far more noisy, but in a very close separation to the carrier frequency. The slow movements belong to my 2 crystal oscillator. Could be temperature, could be power supply stability. Here is the response I see when I run the unit as a filter. It says effective Q 1.73 million, and the gain is only 0.35 decibels. And the phase angle at the peak is about -8 degrees. I want to look at the wideband noise floor, so I'm running Linrod in normal CW mode. So I have the wide waterfall and then I have the S-meter graph. I have calibrated it, so when I measure the level, I read on the average 0 for the two channels, plus or minus very little. I have disconnected my oscillator and instead connected this signal generator, and I have set it to 15.1 dBm, and that turns out to give the same reading nearly as I had with my own signal generator. It differs by 0.05 dB roughly. I reduce the power by 100 dBm. That's the step size I have set, and then I will wait to see what level Linrad will indicate. And I read minus 101 here, so the generator is wrong by 1 decibel, because I trust the digital system of Linrad to compute this properly. There is no distortion to take into account in the system. So I increase by 1 dBm. And then of course I read minus 100 on the S-meter graph. I have increased the sensitivity of my two-channel receiver by about 29 decibels, it seems. But the signal is the same. It is 100 decibels below the oscillator carrier level. So I will recalibrate for this signal to show minus 100. Now the S-meter graph shows minus 100 for the generator signal, which I know is 100 decibels below the carrier from the oscillator when it is running in normal oscillation mode. Here is the noise output from the selective amplifier when there is nothing on the input. And that level is, I can read here, minus 153.5 dBc per hertz. I then tune 200 hertz below, like that, to see what is the noise level at 200 hertz offset from the carrier when it is running as an oscillator. And that comes as minus 178. But this is amplitude noise plus phase noise, so the phase noise should be minus 181 if there is no sideband noise generated in the system, just only the amplifier white noise. I have reinstalled feedback and I have turned down the gain just below the point where oscillations start. And you can see how oscillations are decreasing, and soon there will only be noise. And it is maybe easier to see here. So what I see now is the result from a selective amplifier with a Q multiplier that provides a very narrow bandwidth in which there is noise. And the interesting thing is, what is the noise level on this carrier, or on the center frequency rather, and how does it decrease when I increase the frequency separation? I'm looking on the center frequency at the bandwidth of about 0.25 hertz. The level I see is minus 119 dBc per hertz. Now I look at an offset of 1 hertz, and there I see minus 147.2. At 2 hertz offset I see minus 153 or 52.8 or so. and it's at this position on the peak. And now I look at 4 Hz offset, and there I see minus 158.7. The noise, when I measure as a Q multiplier, comes like this. It's an F-2 noise, and this is AM noise plus phase noise. So phase noise only would be down here if it was an oscillator. But of course this line will depend very much on how much feedback there is. So what I was interested in is what is the slope, not so much exactly where it is. Minus 182 comes here. Then there has to be a F-1 line. And I think it is, if I place it on this point, it will go like this. This point is a bit uncertain. Maybe it is a little bit lower. That means that the curve would go more like that. Or maybe a little higher, but not likely, because that wouldn't fit with this one. So this performance is interesting. But what I don't like is the deviation from the F-3 line, starting at about 0.7 Hz already. This paper was published a week ago, January 26, 2024. IEEE transaction on ultrasonic ferroelectric frequency control. They say their experiments resulted in the single sideband white phase noise levels of minus 182 at 10 MHz. Notably, these noise levels represent some of the lowest ever reported at these frequencies. They provide a figure, and here are the phase noise levels. At 10 MHz, the blue trace. Notably, the wide range noise is much better at 100 MHz. I don't think this really represents what is possible. I have plotted the numbers of the blue trace in my graph here. That's the green points here. As it happens, they fall fairly accurately on the red line that I think represents the oscillator I'm experimenting with. The arrangement with 2 transformers between the first amplifier stage and the second amplifier stage. This is a current transformation, so it sums up as a factor of 11.34. I have removed 4 turns from here, so now there's only 25. That means that the current gain has increased to 13.16. That is plus 0.6 decibels. Not much, but in an interesting direction. I have also removed the 50 ohm load that was sitting here at the output of the feedback port. And that has given a significant increase in gain in the oscillator loop. I then adjusted the coupling capacitors to the crystals to reduce the gain somewhat, to have a output power of about 50 milliwatts. I have also tuned things properly. This inductor should be tuned for minimum noise at large separations, while this capacitor should also be tuned for minimum noise at large separations. And that has given maybe 2 decibels or so. Because I have been fiddling with this without checking that it's properly tuned afterwards. The net effect of this should be more output power and a little less noise at large separations. A larger transformation ratio here means that the impedance that loads the drain becomes a little higher, which means that the crystal will see a little bit higher impedance on the sources, and that should degrade the loaded Q of the crystal slightly. I see no degradation of the noise close to the carrier, and this is the average from 2.2 up to 3.7 Hz, and it's the same as before. I'm running the SDR eyepiece in parallel to look at the wide noise floor. This goes up to 3.7 kHz, and here is minus 182, so it is a little bit below that, but since the imaginary part, the red dots, are very close to where the yellow is, the real part, and there are blue lines here and there, it means that the noise is below what I read from the screen. When I compress the x-axis, it seems that the noise floor is about minus 186, but still it's not really a measurement because the imaginary part scatters along with the yellow line. So I cannot measure it this way, I need other methods. I have found the reason for the noise bursts that I attributed to perhaps the crystal earlier in this video. They come from this capacitor. I have replaced it with one of this kind. That did not solve the problem, so now I have soldered a wire directly on the movable part of the capacitor, so the contact resistance is no longer involved. I have a soldering on both halves of the tunable capacitor, and the wire can move a little up and down, and that doesn't matter.